Well, we're very lucky today to have Stefan Mant here to talk to us. Stefan's an associate professor of computer science at UC Irvine, and he's also Prakar's advisor. His work with Prakar is on video super resolution, but the work he's going to talk about today is pretty different, but also something that is really cool. So Stefan's interesting because he didn't start as a machine learner. He, like many of us, started in a different field. He's did his PhD in condensed matter physics at the University of Cologne. Then he went and did a postdoc at, was it Princeton? Yeah, and there he had the chance to meet someone who was interested in machine learning, and they started working on aspects of stochastic machine learning that were actually using some of the same tools that Stefan had already learned. He found he was pretty interested in it, had a gift for it. Went off to Disney for 2 years, and then to hone his skills further, and then came back to UC Irvine after that to get a faculty position. He has a NSF Career Award, which is a great honor for a young researcher. And we'll be very excited to hear what he has to say today.
Yeah, thank you very much, Chris, and good to see everyone in person, see folks remotely as well. As Chris has already announced, I'm going to talk about a topic that might be a little bit different from like purely climate modeling perspective. It's actually trying to fuse together two seemingly very different fields, namely doing, on the one hand side, deep learning in order to compress data, and then on the other hand, trying to use some of these ideas to also advance climate and Earth systems modeling. So, and hopefully you'll believe me and look forward to how these sort of two different fields connect with each other. And basically the common theme throughout this whole presentation and actually throughout my whole research is that recurrent theme of latent variable models. So who of you are familiar with that concept of a latent variable model? Do you want to raise your hand? Or, yeah, I mean, almost probably half or maybe a little bit more than you. So, but let me nevertheless repeat the main idea. So the idea of a latent variable model is that it's something very naturally occurring in our everyday experience, namely that sort of assuming structure that we cannot immediately observe in our environment greatly simplifies our modeling assumption. Right? So this picture that you should have in mind here is that of an iceberg where only 10% is visible, but without sort of assuming all of that ice underneath, you would have a really hard time explaining that sort of floating mountain, and therefore assuming things that are not immediately evident to see greatly simplify and reduce actually the complexity of the models of our world. And that applies to the real world, but it also in particular applies to machine learning. Now, these latent variable models have underwent an interesting revolution in the last almost 60 years of their existence. So the simplest one is probably a mixture model that just explains a couple of data points by a mixture of Gaussian distributions. Then around 20 years ago, we were all amazed by topic models. Topic models assume basically are mixture models, mixed membership models applied to language. And they were able to identify automatically topics in unstructured text collections, right? And so these topics would automatically emerge. And back then we were like all amazed how that magic would actually happen and why it happens. But of course, nowadays we've then got more and more excited about different things we discovered. For example, variational autoencoders are probably the next thing. They occurred around 10 years ago, and they were probably among the first models that could sort of generate highly structured images, such as, for example, these handwritten digits. But all of that is, of course, dwarfed by nowadays standards. Then, namely, nowadays we're used to seeing these sort of photorealistic images, and we are completely no longer able to tell whether a person or anything else that's being depicted is real or completely obsolete or completely made up, right? And the important thing to notice here is that they're all different versions of latent variable models. So in some sense, this concept is very long lasting, and they only differ in terms of the way, in some sense, algorithmic details, right? I mean, how we do the inference, And of course, there's been a lot of innovation on that in the last couple of years. Right? So, yeah. All right, so this is basically the toolkits that we're going to want to talk about today. But while most of the focus of latent variable modeling, and particular generative modeling of images, is actually arguably in the domains that are more governed by large industry labs, and those large industry labs and tech companies, they oftentimes care about photos they find on the web or modeling text. I want to focus on sort of different themes. Namely, on the one hand side, I want to talk about natural science applications. And then I want to also talk about this relatively new and experimental work where we actually adopt latent variable models to compress images and hopefully replace existing codecs such as JPEG or any existing video codecs using these sort of end-to-end learned approaches. Okay. So let me start by motivating things from the climate science side. And this is actually hopefully what I'm going to talk about most in today's talk for this audience. So this, as you all know very well, and probably better than I do to some degree, there's been a lot of emphasis here in this group and also in other groups in trying to scale up climate modeling to larger scales. And in particular, there's been a lot of excitement about so-called storm resolving models that are now trying to emulate the world on sort of much lower and smaller resolutions than what has been previously possible. And the point I want to make here is there is not a simple agreement about what sort of the best model is, right? I mean, there's a whole zoo of different climate models. They all differ in their underlying assumptions and how they represent turbulence and how they parameterize certain subgrid processes and microphysical processes, for example, droplet formation in clouds and many other things. And so one obvious question that you might ask yourself is, are there any systematic ways in order to kind of really compare these different models? How can we really assess systematically which model is more similar to another model and which one is more far away? In other words, can we learn sort of a distance notion between different climate models? And if we could do that, then we could actually build ensembles of models, and we could potentially know which models to trust more and which ones maybe to trust less, right? Or at least we would know, how to actually assess similarity. And arguably, there's currently a lack of tools that allows us to do that. All right. A couple of years back, we started a collaboration with Michael Pritchard, who was back then also at UC Irvine and still is, but then he's also a director of research at NVIDIA. And some of you might know him. And the data that we looked at back then were sort of vertical velocity fields, snapshots from a particular model called SPCAM. And this is how the data looks like. They're basically just one-dimensional spatial cross-sections. And then they have a vertical component, which is the y-axis here. And this is just altitude or pressure. And then what's actually being depicted are these kind of wind velocities. So whenever something is blue, it's negative, meaning wind coming down, I believe. And if it's red, then sort of wind is coming up. And while the details don't matter so much, what I want to visualize here is that just staring at these kind of snapshots from the different models makes it very hard to just visually compare like which model is more similar to what, right? And this is actually what we feed into our algorithm. This is what our algorithms are supposed to use in order to assess similarity. The only thing I could tell is that probably the top row, or maybe the SPCAM and SAM models, they look systematically different, but I wouldn't be able to tell kind of subtle differences between the other models. Now, how can we do this? How can we actually define similarities between simulators? And here's the main idea. We're taking a completely data-driven head, and we're ignoring all of the known physics about these models. And what we want to do now is we want to assess the similarity between the climate models only based on the data that they produce. Right? And now the model comparison problem becomes that of a distance measurement problem between simulated data sets. Right? Which simulated data set is closer to which other simulated data set? And one sort of favorite distance metric that we like in machine learning is the so-called KL divergence. It's not strictly a distance because it's not symmetric, but it has like all other properties that a distance satisfies. And this is actually defined as follows, as the expectation under a distribution A. And then we look at the log ratio between the distribution A and another distribution B. In other words, the KL divergence is small if two distributions are very close to each other, and it's large if there's some disagreement between both distributions. And interestingly, there's this connection to information theory, and this is actually how it all kind of emerged. Namely, the KL divergence measures the number of access bits that we waste when we try to compress a certain data that are coming from a certain distribution A with the wrong model, namely with a compression algorithm that is tuned towards a distribution B. Right? And so the amount of access bits that we spend there, that's exactly called the KL divergence. So you already see that connection between what we're trying to do here and the connection to information theory and compression. Okay. All right. So with that in mind, I want to give you like a small detour and tell you a little bit about compression, and in particular how you can actually use nowadays machine learning algorithms in order to really practically compress data. Just as a side note, it could be really interesting to explore these models also for compressing climate data. This is something I always wanted to do, but never really gotten the chance to do so. So happy to talk about that. So how does compression work in practice? So compression is always, the main idea is that of lossless compression is first of all that you can completely losslessly take a data set, convert it into a bit string, and from that bit string you can, without any quality loss, you can get the original data back. Now how is that actually possible? Well, the main idea is that you work probabilistically, right? So you assume that your data points, in this example, the red dots, they come from some finite alphabet, or in other words, there's only a countable number of states that these could come from. In this case, you could think of them as points on the grid. And now on that grid, we have a probability distribution that assigns a probability value to every grid point. That's this capital P. And now we take a coding algorithm that is actually called an entropy coder. And the entropy coder looks at the log probabilities of these events, and it assigns them to bit strings in such a way that the negative logarithm of the probability roughly corresponds to the number of bits with which this data point is compressed. And as a consequence, items that are very low probability under your model, they get assigned longer bit strings, but that's fine because those items occur less frequently. And items that have high probability under the model, they occur very oftentimes, and so they also get assigned shorter bit strings. And you can show that this is actually an optimal way to compress your data. Yeah, importantly, you can go back and forth without any information loss. Now, how does lossy compression work? Well, in lossy compression, you typically, as the name already says, you throw away some information that is maybe less relevant. So you cannot perfectly reconstruct your data, but that comes as at the benefit of having an enormously smaller file size. And oftentimes we associate lossy compression with a sort of rounding in some space. For example, imagine now that your data points are not living on the grid locations, but they're actually living in a continuous two-dimensional space. What you could do then is you could basically quantize them. In other words, you round them to the nearest grid location. And then once you have rounded them, you also round the corresponding probability density from which you assume your data came from. And then as a second step, you can just do the typical lossless compression pipeline. And this is, in fact, typically done, right? So lossy compression is usually, first of all, some sort of truncation. And after that, you do lossless compression. And the most important form of lossy compression is called transform coding. The main idea in transform coding is that you don't carry out the quantization in the original data space, but you first transform the data from the original space, for example, pixel space for images, into another space. That could be, for example, in JPEG, that would be the space of Fourier coefficients. And there you perform then the rounding and the entropy coding. Right? And so then after you did that, you can then undo the transformation, for example, the Fourier transformation, and you get like a lossy version of your images back. Now, this plot actually suggests, well, first of all, let me give these different objects names. We will talk always, when we talk about data, we call it X. When we talk about the latent space, we'll call it Z. And the reconstructed data, we call X hat. And as the notation already suggests, that might remind you exactly of an autoencoder. Right? Because in autoencoders, we go from data into a latent space, and from the latent space, we go back into data space. And in fact, it turns out transform coding, as for example in JPEG, and autoencoders are really sort of same thing. It turns out that JPEG really is a linear autoencoder. I want to tell you a little bit more about the technical details of how practical neural compression works, and please bear with me because the slide might be a little bit more technical. So what would we ideally like to do? So we want to learn these codecs end-to-end from data. And to this end, we want to minimize a combination of rate, in other words, the length of these file sizes, and distortion, in other words, the quality loss. And what you can do is you can write rate and distortion as two terms. On the right-hand side, we have the distortion term, namely you have some distance metric rho, which could be a mean squared error, and you measure the distance between your original data point x and your encoded and encoded, quantized, and decoded data point. Right? And you want to make that distortion as small as possible. On the left-hand side, the bit rate is measured by the negative log probability. Right? That's exactly what we just talked about the earlier slide. And this time, we really want to learn the probability metric or the probability density in such a way that this bit rate really becomes as small as possible. And so this becomes an optimization problem over the encoder F, the decoder G, and the probability model P. Now, what are the problems with that? Why can't we just optimize this naively? The first thing is that in machine learning, discrete operations are usually problematic when it comes to automatic differentiation because you cannot backpropagate through a rounding operation. So this is not differentiable. The other problem is that the capital P is actually a probability density over the grid points. So in other words, over the discrete space. And you cannot also not differentiate that with respect to its discrete input. Now there are luckily common workarounds. The first one is that instead of rounding, we actually inject noise. And this is actually a common trick in machine learning that whenever you want to simulate or inform your machine learning model about a rounding truncation that happens then at the test time or inference time, you just inject uniform noise, send it around -1/2 and +1/2. And by that noise injection, you basically tell the algorithm to be insensitive to small perturbations on that length scale so that you can then safely round the result at test time. And in order to work with the discreteness of the probability distribution P, what we can simply do then is we can learn a continuous probability density, small p, that we then sort of integrate in order to arrive at a learned probability distribution. Now, if we combine these ideas, you can kind of get from the upper objective function to the lower objective function. And it turns out that this is exactly the loss function of a variational autoencoder. So I haven't really talked much about the connection between variational autoencoders and compression. I only said that compression, in particular transform coding, looks like an autoencoder. But it turns out that these two requirements of differentiability at training time and learning a distribution in the latent space exactly are the defining characteristics of a variational autoencoder. So you can now actually redo this one-to-one correspondence where the prior of a variational autoencoder plays the role of the entropy model in our transform code, where the decoder corresponds to the likelihood model, and where the encoder corresponds to our variational distribution or inference model. The goal ultimately of learned compression is to improve the trade-off between rate and distortion. I already mentioned that verbally before, but the rate is again the bit rate, in other words, the expected file size average of the data set, and the distortion is the reconstruction quality of your encoded data distribution. And it turns out that you cannot simultaneously be great at rate and distortion. There's this information theoretical trade-off, but you want to be basically as good as possible in this trade-off. In other words, you want to push the rate distortion curve into the origin where you have both a low rate and a low distortion. And a lot of learned compression is now kind of paying attention to exactly that trade-off. So here is a way of looking at it. Those are fairly recent neural codecs and classical codecs. On the left-hand side, you see actually a measure of bit rate, but in this case, it's like rate savings over a certain baseline, which in this case is the best performing classical codec, so higher is better. And on the x-axis, this is actually now quality, so also higher is better. And what you see here are different neural compression curves that correspond to existing algorithms. And what we did a few years ago is we took a certain post-processing optimization trick called stochastic Gumbel annealing that we developed, and don't have really time to go into it, but we actually achieved like a 20% improvement of existing learned compression algorithms. So we significantly kind of pushed that these rate savings by 20% in existing codecs, which was kind of a fairly important improvement in that field of learned compression. Now, in this field, it turns out there's some bad news. And the bad news is that when you look at sort of recent developed neural codecs, you see actually a saturation of performance improvements. So again, looking at quality versus bit rate, you see people came up with more and more complicated compression algorithms, but the performance seems to ultimately saturate at a certain value, right? And the question is that like a fundamental problem, or are we just running out of ideas, or is there maybe a fundamental performance limit that sort of prevents us from achieving better performance than this particular limiting curve? And the unfortunate answer is yes, there is something called the information rate distortion function, and we simply cannot go beyond that information rate distortion function. So let's take a look at what this really means. The rate distortion function in information theory is a property of only your data set, and it gives you a fundamental limit at which you can compress that data set if you're willing to tolerate a certain level of distortion. You can think of that as almost as a generalization of entropy, because entropy, as we know, is sort of the fundamental limit of lossless compression. And so rate distortion kind of generalizes this concept of entropy. Now, what I want to say here is that this is a fairly nasty mathematical object. It's defined as the infimum over stochastic encoders, Q of y given x, such that a certain constraint on the reconstruction is satisfied, and then you're sort of minimizing mutual information between input and output. Again, I don't want to throw buzzwords around me, but mainly kind of it's a complicated thing that you cannot straightforwardly compute. So here's what it's doing. Let's imagine you have, again, the rate and distortion plane, and somebody gives you 2 points on that plane, the green one and the red one. These points correspond to pairs of a certain rate and a certain distortion that an algorithm may or may not have achieved. If you knew the rate distortion function, you could immediately tell which of those algorithms is real and which one is sort of made up, right? I mean, turns out that everything lower than the rate distortion function is just not possible, right? And so knowing that rate distortion function for any empirical data set would be amazing, because we would immediately know how well do existing compression algorithms already perform relative to that curve, and which ones are fundamentally not possible. Now, as I mentioned, there's no analytical simple form of this expression, so it might seem hopeless to compute it. But what we showed we could do is we could actually derive upper and lower bounds, in other words, sandwich bounds of this rate distortion function. And if we could make these sandwich bounds tighter and tighter, it turns out we can basically give an upper limit, which tells us what should be provably possible, and the lower bound should be able to tell us what provably is no longer possible. And the whole uncertainty then remains in this sort of intermediate region. Now, let me be a little quick on that. It turns out that any beta variational autoencoder gives you an upper bound. And the important thing here is that this is really only a property of the data set. So it's not really a statement about any particular model that you use to assess the bound, but it's really any variational autoencoder can, in principle, give you an upper bound on that data set. And it turns out there's also a lower bound, and this is actually probably where most of the work went in. And for that, we had to sort of dig out old information theory papers from the 70s, look into how mathematicians characterize the bounds, and then essentially parameterize these bounds using neural networks. And the nasty thing about that is that there were a lot of constraints that had to be satisfied, so it led to like a non-convex constraint optimization problem that was very hard to solve. Now, how well do these upper and lower bounds look like? So we tested them first and foremost on simulated image data sets, and I'll get to why that is the case later. So imagine you have a pre-trained GAN. Now you can actually generate a data set from that GAN. But more importantly, you can actually now control the intrinsic dimensionality of that data set by just fixing all the dimensions of your noise vector up to a handful, and then only simulating from a sort of handful of dimensions. In this case, we fixed all but 4 dimensions, and this allowed us to simulate from a effectively 4-dimensional data set. We created exactly a 4-dimensional data set, right? Even though the data set itself was actually consisting of dog images, as you could show there. Right? And now we could try to compress this data set and sort of estimate the rate and distortion function. So here, the two red curves on the very bottom, those are the upper and lower bounds of the rate distortion function. So we know that the rate distortion function must be somewhere there in this uncertainty region, which is shaded in red. And now we were interested in how well do we currently do with our existing classical and neural compression algorithms. And it turns out that the classical compression algorithms, they're actually so bad that they're not even shown here. But also the neural compression algorithms, they're still sizably away from that kind of region, which tells us that there's still quite a bit of improvement to be done in order to really efficiently compress, hopefully, real-world image data sets. Yeah. All right. What else is interesting in this field of learned compression? There are lots of other sub-branches that are currently branching out. Instead of only looking at rate and distortion, another focus is on actually making these algorithms also faster. So there's now a third dimension to the trade-off, which is sort of the decoder size, or the efficiency at which you can quickly decode images. And as you can imagine, this is extremely important when you're streaming videos on Netflix. You don't want to wait. You want to kind of decode in real time. And for that, you need really lightweight decoders. But when you make the decoder lightweight, usually your performance drops. And so the question is, how can you maintain the performance but making maybe the decoder 100 times more lightweight? And here we kind of achieved a 95% reduction in speed, in inference speed, while maintaining the good performance of the state of the art. Another frontier in image compression is perceptual compression. So here we also give up on rate and distortion performance alone, because that's a very narrow metric. In fact, if you look at distortion, you kind of really measure the pixel-wise error. But in reality, if you give me an image and you shift it by a single pixel, I wouldn't be able to notice that. Or even 5 pixels translated image, you wouldn't see anything. But it turns out that the mean squared error is oftentimes dramatic. Right? And so in other words, distortion is a very bad metric in order to really measure the distortion, the actual distortion that a human would perceive. And so that opens up this new field of perceptual compression. And long story short, we made some interesting progress here with diffusion models, right? Where we sort of had a latent state, condition on that latent state. We could then stochastically reconstruct these images. And it turns out that these diffusion models get a lot of these details out. But importantly, the details are not exactly the ground truth details. They only look good, right? For example, here, you can see maybe here, in particular, if you look at letters like Suzuki on the motorbike, you see that the algorithms are sort of making up certain symbols here. But if you just look at it, you wouldn't immediately notice it, right? And then you can argue, is that good or bad? But most people would say it's fine as long as it's not symbolic, right? Anyway, it's an interesting line of research. Okay, but that was a longish detour, but let's actually go back to climate science, where our goal was, again, to look at these simulated data sets, right, and then assess the similarity between these different simulators. Now, the first thing that we did in this case is we wanted to do some sort of compression of our data sets, right, in order to answer whether simulation, how far these data sets were apart. And again, as in the other work on compression, we use variational autoencoders for this aspect, right? So we take our data, we encode them, we get a latent state, and from there we try to reconstruct our data sets. As a first sanity check, we checked, what is actually the latent representation that these variational autoencoders learn. And what you see here is a certain degree of disentanglement. So in other words, the variational autoencoder learns to separate the data in a meaningful way without any explicit supervision. So for example, when you look at data taken from over land and data taken from over ocean, you can see actually a slight shift in these distributions, which tells you that sort of the VAE is picking something up about the semantics of the data. And there are also other examples that you see here in these sort of latent state projections. So far, so good, but how does this actually now help us to really measure similarities? It turns out that there's also another ingredient beyond the variational autoencoder, and this is again a compression technique called vector quantization. Now, vector quantization is sort of in some sense an alternative to what I talked earlier about, namely transform coding. And the idea is that vector quantization is basically a glorified way of doing k-means clustering in order to arrive at a discrete representation of your data. And that quantization then allows you to kind of compress the data, but also to kind of assess similarities. So what's the main idea? You have your data manifold here in yellow, right, in some assumed two-dimensional ambient space. And now you do k-means clustering with a very large number of clusters. And every cluster center claims a certain cell for its own, right, for which the cluster center is the nearest neighbor. And with that, you kind of partition your data distribution, and you assign a fraction of each region to one of the cluster centers. And now what you do is you basically take every data point's cluster center as its sort of lossy representation, right? And that gets better and better the more cluster centers you have. It turns out that when you now are interested in measuring Hilbert-Leitner divergence between two continuous distributions, and you work with vector quantization, in other words, you discretize these by quantization, it turns out that the supremum over all possible quantizations gives you the continuous Hilbert-Leitner divergence. And every finite quantization, so any clustering with a finite number of clusters, gives you a lower bound to that through Hilbert-Leitner divergence. Right, so you can only do better if you work with more and more cluster components, and asymptotically, you're sort of guaranteed to converge to the right KL divergence that you're interested in. Now, the nice thing is that working with discrete distributions actually allows us to analytically compute the KL divergence, right? Because that we can just use the formula. Now we have a finite sum, which we can easily compute. The only problem was we couldn't compute the high-dimensional integrals. Now, what we did here is we kind of estimated the KL divergences between the different data sets as a function of the number of clusters. And as you can see, the more clusters we use, the higher monotonically this KL divergence goes. And at some point, it seems to saturate. So it seems that working with only 50 clusters seems to, lead to a degradation in performance improvement. So we can take k equals 50 to be sort of our, like a reasonable way to assess similarity between these distributions.
And are you doing this in the full latent space?
We're doing this in the full latent space, yeah.
Yeah.
And the latent space is like 1,000-dimensional still, yeah. Okay, this is ingredient number 1. Ingredient number 2 is, again, the BAE. So what does it mean in practice? We take the latent space, we cluster it. Here, visually, we only take 3 clusters, but in reality, we can take up to 50 clusters. And then we take kind of the data and coarse grain it by the number of, or the percentage of data points assigned to each of these clusters, right? This is our discrete approximation of the continuous distribution. Now, with that, we can actually now assess similarity between the different data sets. So we've sort of achieved our goal. Now, what you see here is a dissimilarity metric. So white is very similar, red is very dissimilar in terms of KL divergence. It's actually symmetrized KL divergence, which is why the matrix is symmetric. And what we observed is that there's like this subgroup of 6 models that are intrinsically very similar. And there seem to be 3 other models which are very similar from this kind of mainstream cluster. And they're also very dissimilar relative to each other. Right? So lots of reds outside. Now, this was, as far as we know, never explicitly stated anywhere. And so in some sense, it's a new result. And I'm sort of curious about any insights why that is, or any domain input. Now, back to the methodology, you might wonder, again, is 50 clusters enough? Has our procedure converged? I already showed you one other convergence metric. Here's once more the behavior of these sort of similarity matrices as a function of cluster number k. And you can really see that, up to after k equals 20, you kind of barely see any difference anymore between these different patterns. Now, you might wonder, okay, were the variational autoencoders really crucial, or could we have just sort of achieved the same result if we either clustered in the raw pixel space, or whether we did like a linear dimensionality reduction with PCA? And it turns out that this gives nonsense, right? If we vary the number of clusters k, each time we get a completely different pattern, which means that we need probably way, way more clusters in order to see any convergence for these sort of competing methods. In particular, it turns out that k equals to 3 already gives almost the same image as k equals to 50, which made us very optimistic that maybe you can actually get some sort of interpretable insights, because it's always nicer to work with only few clusters. Maybe you can actually assign these clusters to certain semantic meaning. And so, yeah, and this is now what we did. So we worked with k equals 3. And then what we did is we now looked at every point on the Earth. And we basically looked at how dominant each of these 3 different clusters that we found was at this particular point of the Earth. And what you see is there are some emerging spatial patterns, which are very interesting. So cluster number 1 seemed to claim a lot of points that are sort of distributed over land. Sorry. Cluster number 2 and 3 are more over the ocean. And another distinguishing feature then was to look at not only the spatial distribution of these clusters, but also at their average sort of vertical distribution. In other words, are these sort of horizontal wind profile, or the vertical wind profiles, are they stronger at the bottom or are they stronger at the very high altitudes? And again, this led us to distinguish now between clusters number 2 and 3 by discovering that cluster number 2 seems to be very kind of top heavy. So there seems to be a lot of vertical velocity at high altitudes, and this seems to be less the case in cluster number 3. So combining the information from the spatial plots and from these vertical plots, we gave these 3 different clusters names. We identified the first one as continental convection, the second one as deep convection, and the third one as marine shallow convection. One interesting thing that you can now do is you can now simulate a warming climate. And you might wonder, what does this sort of global warming of up like 4 degrees Kelvin in this example, how does this actually affect the distribution of these 3 different clusters? Which ones become more common, which ones become less common, and also how does the spatial distribution of these clusters change? So what we plot here is basically the change in occupancy of these clusters, number 1, 2, and 3. And what we basically see is that for the marine shallow convection, well, okay, let me focus on the second one.
And you've reclustered the data in the warmer climate or not?
No, actually, we didn't recluster because then we couldn't easily compare things. We kept the same cluster centers from before, right? We just recomputed the frequencies. So this is a little overwhelming, as I mentioned. So let's look only at this deep convection cluster. What you see here is that there is this, this heavy, what's it called again? The band. IPCC band, right? That carries a lot of moisture right across the ocean, and this seems to become stronger. And overall, this sort of deep convection seems to intensify overall, right? Which is apparently, consistent with what we expect for global warming. Another interesting thing you can do is you can now look again at these 3 vertical profiles, and you can see what actually happens to the vertical distribution before and after global warming of these 3 different clusters. And what you see again, very dominantly, again, looking at the deep convection cluster, which is very top heavy, is that not only does it become more frequent, but it also gets more intense because like the whole profile shifts upwards, right? The dash curve is the result after 4 degrees of global warming, and the solid curve is before 4 degrees global warming. So basically deep convection becomes deeper and more frequent in certain regions. Yeah, notably, all of this was sort of coming out completely unsupervised without any domain insights, only from the analysis and only working with a sort of interpretable number of clusters. All right, any questions so far? Because now we'll probably switch topics and I'm not insisting on covering more. Any questions about anything that has been talked about so far?
Did you try this on other fields than the vertical velocity? I understand why the vertical velocity field is a good field to use, but you could use, for instance, fields like cloud condensate, for instance.
Yeah, unfortunately not, right? I mean, yeah, I think this was sort of like a steep learning curve for Griffin, who was an amazing student, right? He had to sort of simultaneously pick up on machine learning and on Earth system science, and I think we only studied like one modality. We had one project where we sort of had like 3 different input modalities, but we didn't do the full analysis.
An interesting feature of this is I get the results, and I think in particular that SPChem and SAM look different than the other models. Is particularly robust. In Python, I guess the differences are a bit more subtle. But what was interesting in the Diamond project is, depending on what you looked at, different models looked more similar to each other, and so there wasn't one. It wasn't robust to the field, it seemed like.
Well, that's interesting.
And so it would be interesting to see if that came out through this unsupervised approach.
Yeah, no, that'd be
Next
really
project.
Yeah.
that'd be really interesting.
Yeah.
Yeah, thanks for the feedback. Yeah.
I had one question on the rate distortion trade-off you were discussing earlier. When you're working to learn what the bounds were for whether or not you were close to the limits of the compression for an algorithm, you said you chose a dimensionality of, or you ended up at a dimensionality of 4 to actually do the analysis. I'm wondering sort of how that number arrived at one, whether or not there's a lot of variance in between when you kind of increase or decrease, and I'm assuming the trade-off is compute or something that kind of determines what that.
Yeah, that's a good comment. I was really rushing through this part. So the reason we picked k equals 4, it turns out that while the upper bound is very scalable and robust, it turns out that this lower bound, where I mentioned that it's like a nasty non-convex optimization problem with constraints, it turns out that this is not as scalable, and basically you only get up to 100 dimensions. And there's an intrinsic difficulty associated with estimating lower bounds to mutual information, which is actually well known. So this is why we looked at the most realistic but intrinsically low dimensional data set that we could find, which was a GAN generated image. So you can actually see that the gap between upper and lower bound widens if you play with a higher intrinsic dimension. Yeah. All right, so let me maybe cover another 5 minutes. I just want to go quickly over sort of unless Prakhar, you've already talked about your research, then it might be boring.
Not in detail. But
not in detail. I just want to quickly touch on one more direction that we covered at UC Irvine, which again connects diffusion models and climate modeling. And this is basically this idea of using diffusion models for video forecasting. So many of you have already heard about diffusion models in the image space, right? So you take an image, you add a little bit of noise until the information is completely destroyed, and then you're trying to invert this process stochastically so that you, for every 2 adjacent stages of noising, you try to sort of undo that last bit of noise injection. In other words, you want to learn the posterior of the noise, of the noising process, which is the denoising process. And once you've learned these stepwise posteriors, you can basically then run them in the opposite direction, and you can kind of create structured images from pure noise. Now what Prakhar and another student, Rihan, and I worked on is kind of extending this idea to video modeling. And I can proudly say we were the first to publish on this. There's another Google paper, which is very well known on this as well. Those 2 papers were sort of concurrently developed. But here's what our idea was. Our idea was to formulate this as an autoregressive process, right? So we take a video sequence, xt minus 3 to xt. We feed this video sequence into a convolutional LSTM, and this convolutional LSTM makes a mean prediction, like its most likely belief for the next frame. Now, the problem with that is that the next frame will be typically blurry because the future is multimodal, right? I mean, an object could move in any other direction, and the machine learning model needs to find a compromise about what it thinks to be most likely, and this compromise image will typically be a blurry image. Now, to undo this blurriness, we draw on diffusion processes. So the idea is now to let the final predicted frame be the composition of a deterministic forecast plus a stochastic residual. And the stochastic residual is the outcome of a diffusion process. And the diffusion process itself is conditioned also on the history. Right? So this is roughly the model. Here's another way of looking at it. And it turns out that this approach leads to really nice both quantitative and visual results for natural video. You can compare against GAN baselines. You can compare against the variational autoencoder baselines. And it turns out that diffusion models are in some sense like best of both worlds in terms of getting high quality sharpness, like good perceptual results, but then also being good predictors in terms of PSNR. Again, what Prakhar is doing, and I don't want to talk too much about it because his results are much more interesting. He's now currently applying these approaches to weather modeling and climate forecasting. So those are some really old results. And it turns out, as I already said, also the stochastic forecasting properties of these models are really good. So this is all I wanted to mention. It's a little bit disconnected. Maybe it's time to wrap up. So we talked about generative models, in particular latent variable models. There's much activity and much interest in that in companies. Lots of data sets are being modeled, but most of them are sort of either natural images or text. And I think there's a huge space of applying these models in scientific domains. And also data compression, which at the moment is very sort of experimental. We talked about neural compression, where the goal is to learn compression schemes in an end-to-end fashion. Could be really interesting also for scientific data. I don't think many people talk about it, but nobody has really done it. Yeah, and I kind of really talked only about certain highlights in this space from my group. I also talked about climate science applications, where we talked about comparing different climate models and understanding these comparisons as distribution shift measurements. And we learned that variational autoencoders in conjunction with vector quantization can be very useful and viable tools here in this space. And also with k equals only 3, we get interpretable signatures of known effects of global warming. Yeah, I think compression has a lot of things to offer, but for this audience, I think it could be interesting to talk about compressing large-scale simulation data sets. And with that, I would like to wrap up, and thank you very much for your attention. I'm here for your questions. And I think you already asked quite a few questions, so.
Sure. Well, let's first see if there's any questions from the remote audience. Is there anyone out there? If so, just unmute yourself and have at it, or put it in the chat, and maybe Stefan will see. Okay, well, stone silence from the remote audience. Any other questions from people here?
I have a more philosophical question.
Uh-huh.
So you were talking about when we do compressions, and then the example would be like the Suzuki, the brand, the names, the characters are like kind of distorted or like off by a couple pixels, and human eyes don't even notice. But when applied to like a climate model, right, it could be Seattle versus Portland, so it's two completely different cities that have to do different plannings. So how would you?
I think it's a very interesting and open question to some degree. I mean, on the one hand side, I agree with you that in science we're really maybe even more quantitative in some sense, right? We really want to kind of preserve as many relevant details as possible. On the other hand, I mean, you could still argue that maybe mean squared error is not the right metric, right? I mean, if your whole weather prediction in a discretized pixel landscape is shifted by 1, maybe that's still a pretty good forecast in some sense, right? Maybe you shouldn't pay as much attention to that either, right? So I think you can still argue that maybe even in scientific domains, you might need different metrics, right? And maybe, and the nice thing about diffusion models as opposed to GANs is that they're not really just trying to mimic the data distribution, and they're not only trying to collapse to a certain region in the data manifold, but they really want to cover the whole distribution, right? And they're really measuring likelihoods. So you could still argue, I think, that maybe even there it might make sense. But I agree about the concerns. The other nice aspect is that these diffusion models for compression, they actually enable stochastic reconstruction. So basically, you could simulate multiple reconstructions, and then you have a notion of uncertainty,
right.
Which you don't have in the traditional compression algorithms, actually. Yeah, it's actually a good thing, right? Usually in compression, you never care about uncertainty if you have stochastic decoders, but maybe in science you do. Yeah.
And how reliable is the stochasticity that comes out from that as a representation of that in the original data set? And how do we know?
Yeah, that's a great question. Yeah, I don't have a quick answer to that.
Because that's, I think, a really important issue for the science applications, at least the way.
Like the overall uncertainty calibration, you mean?
Yeah.
Okay.
And there's also another piece of quality loss. I mean, just because you have this discrete latent space, the discrete latent vector, there alone you already had to throw away some information, and that's no longer captured in the uncertainty assessment. So yeah, it only gives you like a partial uncertainty estimate of what kind of information may have gotten lost, but not the full answer.
Also, for instance, work like Solvers is using latent variables in a prognostic sense. In other words, try to predict the evolution of latent variables instead of just describing the system at individual times using latent variables. And I've actually been surprised how little work I've seen in that, because it seems like an extremely obvious thing to exploit more. Is there some reason for that? Is there some gotcha about using latent variables in a predictive sense? Or
I'm not completely sure about.
well, so for instance, if the original way of thinking about this, for instance, is you have a phenomenon like ENSO. It can basically be described as sort of a coupled oscillation of the atmosphere and ocean. So it involves, spatial fields varying over many places, lots and lots of apparent degrees of freedom, but really it has sort of 2 degrees of freedom, if you want. It can be described in terms of a principal component analysis using 2 degrees of freedom. So you can imagine making a predictive variable of ENSO using basically 2 degrees of freedom, namely the amplitude of those 2 PCs. But there's a lot less work trying to use latent variables, say, derived from a VAE, in a predictive sense to predict the evolution of a system to make dynamical equations.
Yeah.
Is there some reason for that, or is it just something that?
I mean, there are temporal VAEs, if that's your question.
Yeah.
There is some work on sequential VAEs. It's like, it's kind of a smaller. I would say in general, machine learning, people looking at temporal or dynamics, that I would say probably that's only 5% of the community looking at sort of dynamical modeling. But there are definitely lots of people who worked on sequential VAEs as well.
And are there significantly different algorithms for optimizing that behavior?
Not necessarily, I think it's all very similar. I think you have to think a little bit more deeply on how you incorporate context, right? Temporal context. Do you want to work with a fixed window size, or do you want to use for example, an RNN, or maybe do you want to use a transformer? And then also, should it be translational invariant, should it be convolutional or fully connected? So there are many design choices there. It makes these models a little bit more complicated than regular VAEs, but there's definitely lots of work on sequential VAEs. And then the whole idea of these diffusion models is that because VAEs are generally blurry, that the temporal diffusion models could be even better than that, right?
I had a question along the lines of distortion again. So one thing that's obviously important for scientific data is that a lot of times there's underlying physics that have constraints about how the variables are related to each other that would not necessarily be followed after data is destroyed and you reconstruct something compressed. I'm just wondering how you handle, or what ideas there are about handling these sort of physical constraints in the compression space.
Yeah, that's a great question. I don't think that lots of people have looked into this yet, right? I think you could potentially design your own loss functions that sort of, I think you probably need to convert the hard constraints into soft constraints, with just adding like another Lagrange multiplier. But then this could be your VAE loss, right? And then you could still do compression, moving away from mean squared error to something that's paying attention to the more physical degrees of freedom. No, definitely. I mean, I'm not aware of a lot of work in this domain, and maybe that's in part because these first generation of compression algorithms were like 100 times too slow to be practical, but now with parts of our own work, they're like now really in the same ballpark as classical image codecs. So it could be really promising, I think.
I'm wondering if you have any thoughts on how to evaluate the perceptual quality of reconstructions for physical data or climate data.
Yeah, that's a good question.
Because I agree that the MSC might not be
Yeah.
It's probably not the best metric to evaluate performance.
Yeah, I mean, maybe you could just, I mean, we just had a discussion about how we evaluate kind of super resolution for climate. I mean, you could look at sort of power spectra, which is something like, probably might know this, like Fourier transformation over space. See if the right, the reconstructions have the right frequencies as real world images, right? Whereas like a blurry model will probably have like a cutoff at some point where all the high frequency details are zero in the reconstructed images, where the real world images have a lot of high frequency details. So I think in this metric, like the diffusion-based compressor might be clearly better. But yeah, probably have to come up with your own metrics that are relevant in a certain domain. The good news, like the good thing about this diffusion approach, you don't hard code it in there, right? I mean, you just learn the conditional data distribution. If you don't optimize specifically for a certain metric, you hope that it automatically inherits these aspects of the data when you reconstruct. Right. There's actually another interesting connection somebody mentioned. I think you mentioned the intrinsic dimensionality of climate data that might be much lower. I think they could also connect to the rate distortion assessment, right? I think if a data set is very compressible, if it has a low intrinsic dimension, you should be able to see it also in these rate distortion curves. So maybe they could also tell you interesting physical insights about the true dimensionality of high-dimensional data sets.
Yeah, it would be quite fascinating to explore more. Okay, well, we're pretty close to the top of the hour, so I think if there's any further discussion, feel free to email Stefan or contact me and I can contact him. But anyhow, thanks very much for listening, and thanks very much to Stefan for a great talk.
Thanks.
Okay.
You.